This is part 5 of a series on autoencoder. In this video, we will take a detailed look at the variational autoencoder. A variational autoencoder is a type of likelihood-based generative model. In this video, we will look at how a variational autoencoder model learns from data and how the trained model generates data. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. First, let's look at the basic concepts and network architecture of variational autoencoders. Next, let's look at the loss function for training the network. How to implement the network will be covered in the next video. The variational autoencoder was first introduced by Diederik Kingma and Max Welling in their 2013 paper titled Auto-Encoding Variational Bayes. The authors of this paper introduce a stochastic variational inference and learning algorithm that scales to large datasets and, under some mild differentiability conditions, even works in the intractable case. We will look at the variational autoencoder presented in Chapter 3 of the paper. And let's derive the loss function required to train a variational autoencoder model. Now, let's look at how a variational autoencoder works. A standard autoencoder works as follows. The encoder typically reduces the dimensionality of the input data X to produce a latent vector Z. The latent vector Z is represented as a single point in the latent space. In this example, the image of the MNIST digit 5 is mapped to this point in the latent space. And the decoder reconstructs the original data X from this latent vector Z, which is a reduced representation of X. In a variational autoencoder, the input data X is not represented as a single point in the latent space, but as a single probability distribution. It is assumed to be a multivariate normal distribution. The encoder outputs the mean and variance of this normal distribution. If the number of neurons in this layer and this layer is 2 each, 2 means and 2 variances for a two-dimensional normal distribution are output. In this example, the MNIST image of the digit 5 is mapped to a two-dimensional normal distribution in the latent space. That is, any point in this area could be a latent representation of the digit 5. A latent vector located at the center of the distribution is most likely to be the digit 5, and the further away from the center it is, the less likely it is to be the digit 5. And we sample a single latent vector Z from this distribution. The decoder reconstructs the original data X from the latent vector Z sampled from this distribution. This is the basic idea of variational autoencoder. However, there is a problem with this architecture. This sampled latent vector is a numeric vector consisting of values of numeric type. Then, the gradient of the loss L will not be propagated to the lower layers during the backpropagation process. This causes the encoder's parameters not to be updated. To solve this problem, the authors of the paper proposed a reparameterization trick. We sample epsilon 1 and epsilon 2 from the standard normal distribution. And we compute the latent vector Z using the following formula. The latent vector Z computed in this way is similar to that sampled from this distribution in the figure on the left. Let's say that the parameters of this layer are W mu, and the parameters of this layer are W sigma. And the input to this layer is U, and the input to this layer is V. Then this formula can be written as follows. Now that the latent vector ZID is represented as parameters of the network, the gradient of the loss L with respect to the parameters can be propagated to the lower layers. This is the reparameterization trick presented in the paper. The key advantage of a variational autoencoder is its generative capability. A variational autoencoder learns to model the probability distribution of the input data, so it can generate new samples that are similar to the original data. For autoencoders for dimensionality reduction, after training is complete, only the encoder is used to obtain a reduced latent vector of the input data. For variational autoencoders, after training is complete, the decoder is used to generate data similar to the input data. For example, if you want to generate multiple images similar to the digit 5 in MNIST, you first input the digit 5 into the encoder and find the mu and sigma. Then, by randomly sampling epsilon from the standard normal distribution to obtain z and feeding z into the decoder, we can generate an image that resembles the digit 5. By sampling epsilon from a standard normal distribution multiple times, we can generate multiple images that resemble the digit 5. Next, let's construct the loss function required to train the variational autoencoder model. Since variational autoencoders are probabilistic generative models, the process of creating a loss function is somewhat complicated. So let's go through it step by step. Let's say that the parameter set of the encoder is phi, and the parameter set of the decoder is theta. Our goal is to estimate the true parameters theta star and phi star such that the p theta of x is maximized. If the input x is like this, then the probability that the output will be x is like this. The higher this probability, the more similar the input and output data are. Given a joint distribution over x and z that depends on theta, the p theta of x can be expressed as the marginal distribution of x by summing the joint distribution over all possible values of z. And the joint distribution of x and z can be written as follows by Bayes' theorem. Therefore, the p theta of x can be expressed as follows. We assume the p theta of z is the Gaussian distribution as a prior in the latent space. And we can use a neural network, a decoder, for this conditional distribution. However, the integral of the marginal likelihood is intractable. That is, we cannot evaluate or differentiate the marginal likelihood. This time, let's use Bayes' rule to express the p theta of x as follows. This expression is also intractable because the denominator is intractable. So how can we express the p theta of x in a tractable way? To this end, let's introduce a recognition model, the probability q phi z given x, an approximation to the intractable true posterior, the probability p theta z given x. The probability q phi z given x is an encoder model. The right-hand side is intractable, but the left-hand side becomes tractable if we use an encoder. Then we can express the p theta of x in a tractable way. Again, our goal is to estimate the true parameters theta star and phi star such that the p theta of x, or the log p theta of x, is maximized. According to Bayes' rule, the p theta of z given x can be written as follows. And the KL divergence of q from p can be expressed as follows. Substituting this into this expression and rearranging, we can rewrite this equation as follows. Rearranging this equation gives us the following expression. Here, Q is a probability distribution, so this is 1. Then, the log p theta of x can be finally written as follows. Our goal can be achieved by maximizing the equation on the right-hand side. The first term is the KL divergence of the approximate Q phi z given x from the true posterior p theta z given x. Since this KL divergence is non-negative, the second term is called the variational lower bound. This is the equation 1 presented in section 2.2 of the paper. This equation can be written as follows. Therefore, we can achieve our goal by maximizing the variational lower bound. Let us denote the variational lower bound as L. Substituting this into this expression and rearranging, we can rewrite this equation as follows. Since Q is a probability distribution, this summation can be expressed as expectation. And the second term is the negative KL divergence Q phi z given x from p theta z. This is the equation 3, presented in section 2.2 of the paper. Our goal is to maximize this L or minimize the negative L. Then we can create the following objective function. The first term is the negative expected reconstruction error. And the second term, KL divergence, can then be interpreted as regularizing phi, encouraging the approximate posterior to be close to the prior p theta of z. So far, we have created an objective function like this. Now let's use this to generate the loss function needed to train a variational autoencoder. The input x is d-dimensional, and the latent vector z is k-dimensional. In this figure, z is shown as two-dimensional, but in reality, it is multidimensional. Next, we assume that the prior p theta of z follows the standard normal distribution. And we assume that the approximate posterior q phi z given x is normally distributed with mean mu and variance sigma squared. We approximate the expected reconstruction error through a sampling technique. We sample z from a Gaussian distribution L times per single data point and compute the average of log p theta to obtain a rough estimate of the expected reconstruction error. Here L can simply be set to 1. The authors of the paper said, "In our experiments we found that the number of samples L per data point can be set to 1 as long as the mini-batch size M was large enough, e.g. M is 100. Then we can simply write the expected reconstruction error as follows. Now let's deal with the regularization term. When P and Q are normally distributed, the KL divergence of P from Q is as follows. If Q follows the standard normal distribution, mu Q is 0 and sigma Q is 1. Since we assume that p theta of z follows the standard normal distribution, our KL divergence can be written as follows. Here k is the dimension of z. That is, the number of mu and sigma output from the encoder is k each. Next, let's find the maximum likelihood estimator when the distribution of the input data x is Gaussian. That is, this is the case that the elements of data X are real values. The output of the decoder is Y, which is an estimate of X. Y is a function of Z and theta. If theta is WB, Y is computed as follows. Here G is the activation function. Then the loss is calculated in terms of X and Y. The probability P theta X given Z can be defined as the product of all Gaussian distributions for each element of X. We have already seen this expression in the linear regression series of machine learning tutorials. Then, the log P theta X given Z can be written as follows. Here D is the dimension of X. Substituting this into this expression, we get the following expression. This is the reconstruction loss using mean squared error. And the regularization term, KL divergence, is as follows. This is the final regularized loss function when X is Gaussian. Next, let's find the maximum likelihood estimator when the distribution of the input data X is Bernoulli. That is, this is the case that the elements of data X are binary valued. This is also the case for standardized MNIST images. The probability P theta X given Z can be defined as the product of all Bernoulli distributions for each element of X. We have already seen this expression in the logistic regression series of machine learning tutorials. Then the log P theta X given Z can be written as follows. This is binary cross-entropy. So the reconstruction loss can be written like this. And the regularization term, KL divergence, is identical to the expression on the left. These are the loss functions for variational autoencoders. Both functions are tractable and differentiable. The loss function we created on the previous page is for stochastic gradient descent using a single data point. The loss function for mini-batch gradient descent is expressed as follows, where m is the mini-batch size. We will use this expression when implementing a variational autoencoder in the next video. So far, we have looked at the basic concepts of variational autoencoder and created loss functions. In the next video, we will implement a variational autoencoder model using the loss function.